thank you for inviting me and thank you for joining for this talk. We will stay at these specific rise and we will now take a closer look at the magmatic system that Jean-Arthur was talking about. So these specific rise, it's a segment of the mid-ocean ridge system that is located about 2,000 kilometers away from the west coast of Mexico. It separates two plates, the Pacific plate and the Cocos plate, at the rate of about 110 millimeters per year, which makes it one of the fastest spreading center and one of the best studied, actually, portion of mid-ocean ridge system. Here, two plates are separating and giving rise to new oceanic crust. Here, I'm showing the diagram of typical oceanic crust that is accreted at the EPR, containing the upper crust, the lower crust, and a very well-developed magmatic system that is topped by a shallower magma body that we are going to look at today, which we call axial magma lens, or AML for short. So why we like to study the EPR? It's very dynamic and it has experienced eruptions. We have documented eruption from 1991-92, 2005, 2006, and most recently, about a couple of months ago, we had a new eruption on April 29th. In fact, we had researchers who were on Alvin collecting some gas samples. And this is the film that was taken from Alvin around Teak event along the ridge axis. And on April 28, everything looked fine. Nothing was indicating that an eruption is approaching. So when they went the next day, on April 29th, they saw completely different environment. Everything was covered by newly erupted lava and basically everything was destroyed. So this is one of the, this is the first witnessed eruption on mid-ocean ridge system. However, I'm not going to talk today about this last documented eruption. I will mention towards the end some of the interesting things that are coming up. What I want to focus on today in this talk is what is the role of the magma body architecture in volcanic construction and evolution, and where and how dikes nucleate. To tackle these questions, we are going to use seismic data, 3D multi-channel seismic data that we collected in 2008. So here we have the bathymetry map on which we superimposed ship tracks of Marcus Lancet, the ship that has capacity of towing 4 6-kilometer long streamers and collecting 3D seismic data. This is the box, this dashed box is actually the outline of the eruption area. And during the survey, just to mention that we covered about 40 by 30 kilometers of the subsurface. Here I'm showing the 3D view of the seafloor and the first image of seismic section that we obtained right after the cruise, where we can see the reflection of the seafloor, we can see the contact between basalts and dikes, and we can see this shy little guy, the AML, so to actually improve and see it much better, look at its shape, I teamed up with colleagues from Shell, from industry, and used their advanced 3D elastic fulviform inversion code to obtain velocity model, which then I used to obtain properly processed 3D volume. And some of the images extracted from this volume showing in this slide, and you can see the AML that is imaged. In some places it's relatively simple, in fact, but in some places it's very complex, very segmented, disrupted, and so on. To actually best appreciate the variation of the morphology of the magma body, it is best to actually look at the extracted horizon from the axial magma lens, which is shown in this panel here. The colors are representing depth beneath the sea surface, so we can preserve the original shape of the magma body, with the red colors representing the shallow parts of the magma body, whereas the deep blue or dark blue or black are representing the deeper parts. So just for the reference, this deeper part is about 3 kilometers below the seafloor, and red is about 1.4 to 1.5 kilometers below the seafloor. These are the side views from this 3D volume of the same magma body. And one of the key messages that I want to convey by this slide is that magma bodies are not flat. So even in this diagram that I showed in previous slides, I indicated them as ellipses, almost regular, but in fact, magma bodies have their topography, which is important for dike nucleation and many other processes that we are working on. For the time constraint, I will focus today only on the area that is sitting right beneath the dominant portion that contributed the most to the 2005-2006 eruption. So here we have the seafloor bathymetry on which we superimposed the outline of the lava flow that is mapped using bathymetry at 1 meter resolution, thanks to our colleagues from the US. And then here is the plan view of the magma body with the same outline, just for comparison. Luckily, during 2005 and 2006 eruption, we had OBSs, ocean bottom seismometers, on the seafloor that recorded the signal from the eruption that we will look in a couple of slides from now. But before we go and look at the eruption, I want to focus on another feature that I find very interesting, and that's this deep, I call it westward dipping channel. Before we go and zoom in, I want to actually look at the bathymetry a bit zoomed out, in fact. So we still see the East Pacific rise, but next to the East Pacific rise on its western flank, we see quite a bit of seamounts that belong to Lamont Seamount chain. And in fact, from the shipborne bathymetry data, it has been speculated that this feature here might be actually the current location of the buildup of the current seamount. And in fact, when I went and picked the seafloor horizon from the seismic data, I started seeing circular shapes feature with a dome inside, which is witnessing that there is activity, and this may be actually location of the current mantle melt anomaly. I call it here a nascent caldera, but that may not be geologically appropriate term. It is surrounded by off-axis magma lenses that were previously imaged in the lower crust, outlined in this dashed white line. So what we think is happening here, we have a deep or a relatively deep upper mantle melt anomaly that is bringing melt and feeding these off-axis magma lenses. And one part of this melt is actually going vertically above, resulting in new seamount construction. But then one part is also deflecting and bringing some extra melt to the ridge axis. And probably this is actually the channel, the part of the channel that we are imaging is actually the connection between the two. This is not only from the seismic point, we also have evidence from geochemistry. And basically, because we are seeing recurrent eruptions in this particular area, so all 3 eruptions that we documented are happening at 950 degrees north. We think that it's really the fact that we have this extra melt that is overpressurizing the system and resulting in recurrent eruptions. Another feature that we have in the main magma body is this depression or trough. I outlined it just for you to see it. And we think it's actually the dike nucleation zone. There are several lines of evidence why we suggest that this could be a dike nucleation zone. First, we have, you remember that I mentioned that we had OBSs deployed. One of the records, there were events that were collected on January 26, 2006. That's considered as the last pulse or last determination of the eruption event. And these events are plotted here. The difference between the gray and black dots are just in magnitude. So the strongest are actually the black ones, the 50 strongest events. And when they are plotted in a profile view from AA prime and BB prime, you can see that most of these events are actually originating or falling at the level or depth of the axial magma lens, suggesting that probably what we are recording is the nucleation of the dike from the eruption. Another very interesting thing is that the deepest part, the northernmost part of the depression, which is about 72 meters deep, is perfectly aligned with the innermost plate boundary zone, which we call axial summit trough, that you can see in this high resolution bathymetry map. This is not the case in the southern part, where this depression is shifted to the east with respect to the AST. And in fact, when there is a shift between the AST and the trough, we have the intrusion of shallower magma bodies. So this part, this panel is showing the main magma body, but then we have intrusion of a shallower sill that is sitting at about 150 to 200 meters above the main magma body. So what we think is happening here in this northern part, deepest part, we have perfect alignment between the AST and the trough. And so the dike was actually going easily vertically above, and the most of the lava flow was placed in this area. However, in the southern part, this is not the case. We have a bit of a shift of the trough with respect to the AST. So some of the melt was mobilized and lava and placed on the seafloor, but because there was not enough pressure, there was some of that material was actually intruded as a shallower sill. And we think that, or actually its depth corresponds to conductive boundary layer, the maximum depth of the hydrothermal circulation flow. Another very interesting point here is that we have, for the first time, we can actually do a proper comparison of what we observe on the seafloor and what we see in the subsurface. So I was able to calculate the volume of this trough and compare it with the volume of the erupted lava, because we have very well mapped lava in place during the 2005-2006 eruption. And we estimate the volume of dikes when the dikes are assumed to be 1 meter wide, and then the volume of the shallow magma body. And they compare not at the level of the magnitude, but really almost at the exact number. Now we looked at the distribution and variation of this magmatic system in 3 dimensions, but we don't know how this magmatic system changes in time. So we want to know the 4th dimension, and for that we are going to collect now in January, February next year, go to repeat actually the survey in the same area. Now we know that the eruption happened, so we will be sampling magmatic system between volcanic cycles. So we will see how the magmatic system, its shape changes with time, from 2008 to 2026. Right now, Lancet is in the area, so we hope that this week there will be 5 OBSs deployed in the area. So we hope that the eruption is a bit longer time event, not one-day event, and we will record some seismicity and recover these OBSs when we go to actually collect the 4D data. And with this, I would like to thank you and take questions.